z inside, but it doesn't immediately know the entirety of z, because our cost is determined by how many times we query z.
So the algorithm is uniform with respect to z. It doesn't change with z, obviously.
No, it doesn't.
Okay,
so maybe this is the way to think about it. So like the trivial thing to do here would be like read all of z, and then you could like compute g inverse of z, and then just simulate the communication protocol, and you're done. The point is you can do like much better, and like the amount of queries you have to make only depends on the length of the communication protocol. It's like the length of the output, not on the not on just like reading the entire thing and saying I'm good.
I think so. G inverse z would be
it's like the set of all pairs alpha y such that I guess y sub alpha I equals z sub I for all I between 1 and k.
Oh, I see. So okay. I don't know. This is interesting for me. Then I have to do a distribution over those. And t-factor, yeah, I'll think about it.
Now I'm going to talk about, so like, if we have this, how are we going to get that? Which is, I think, what everyone's waiting for. Let's call that big star. Yeah, so we have a randomized communication protocol, and view this as a distribution over deterministic protocols. Then so these are going to be bounded error. That's it. Yeah, this is just what we have, and then we're going to run this algorithm. Let's call this. We draw a deterministic communication protocol based on our distribution, then apply the theorem. Yeah, so that's all we're going to do. We're just going to get a randomized thing and output the last bit. And because we made the assumption earlier that the last bit of our transcript is always going to be the answer to F. And this is like approximately, so we can just compute the probabilities. We ignore the little y factors. Okay. F, G. So I'm just writing what this is computing, and now I bring out like the expectation on alpha y. And by that, we actually know this is going to be less than equals 1/3. Yeah. So that gives us a bounded error deterministic, a bounded error randomized, like the decision tree thing that computes F. Yeah. So
So you said ignoring, is that big O one or little O one?
oh, it's little one.
That's little one? And is that also true in the theorem statement? Because then I'm happy to ignore it, otherwise I'm little.
That's little one.
Yeah, they're both little. They're both
Yeah, the theorem statement.
all those are little? Okay.
Little.
Golden.
And I guess we don't really need it to be little one. If it's like less than 1/6, 1/6 is
Yeah.
one.
If it's less than if it's less than half, I guess.
Yeah.
Bounded for it.
Somehow the way you do the proof, it's 1 over poly k, and it doesn't really help you to try to get better.
Yeah. Yeah, so I think, what was I going to say? Alright. Oh, this is yeah, so we just actually just draw, we just apply that theorem to our deterministic protocol that we got from this distribution, and that says that it's like sufficiently close to the real distribution that if we just output the last bit, we're actually just good to go. Yeah.
Oh. So it doesn't really, so outputting the whole transcript is kind of, in a sense, it's really not necessary, I guess, right? Is it just sort of like you naturally will do that since you're simulating are you kind of like simulating the communication protocol like step by step, so it kind of comes out naturally, but like you really only care about the last bit, I guess.
Yeah, you really only care about the last bit, but in order to like actually get something that you can say things about and make it like more naturally follows that we have to.
Oh, I see. Yeah, because you want to say the transcripts are close, and just saying like the last bit, that's not very much.
I guess this is sort of a somewhat stronger theorem than the final.
Yeah, it is. Yeah, so they're not equivalent, I guess.
Yeah. Okay.
Nice switch.
Then I think Brandon's going to talk about how to actually prove that.
Yeah. All right. Thanks, Xinyu. Yeah, thanks. So, right. Yeah, so this, by the way, yeah, it's the number of queries you made is like the communication over log n, so that's what you just get if you divide log n over n. Good, okay, so let's stare at this very complicated theorem that we have to try to prove. And, yeah, I mean, somehow, to summarize it, so many notes here. Yeah, so there's like some fixed z, a k-bit string that's like hanging out here. And the theorem says that like some querying algorithm, what can it do? So for every different string z, it generates.
Sorry, I should ask earlier. You assume a uniformly random alpha y in G in this D.
Yeah.
Are you saying that it's uniform because like you're given a uniformly random alpha y?
No. So actually, the reason that the distribution here, alpha y, is like uniform on a preimage of z, it's to make this theorem easy to prove. In the end, we see it's just enough. Any distribution, any distribution on like the preimage of z would have been okay here. But we're only able to prove this theorem in the case where it's like the uniform distribution.
Yeah. But z not.
Pardon?
Z not.
Yeah. Right, so like again, there's 2 to the k different possible values for this string z, and like this query algorithm doesn't know what, at the beginning, like there's 2 to the k different possibilities for what z is from the query algorithm's point of view. And like it's annoying for the query algorithm because each different possible z that it could secretly be generates a different probability distribution on the communication inputs. So it's like it has 2 to the k different input distributions for the communication problem. And like it kind of has to, you know, output a simulation or like a draw from like what the transcript would be under this distribution on inputs. But it doesn't even know what is the distribution on inputs it's trying to simulate. There's like 2 to the k different possibilities. Like still it's got to do that. So it's in some trouble, but it can actually, as you'll see in a second, it kind of can do some stuff. And then after a while it'll be really stuck. And it won't be sure how to like start generating like the next bit of the transcript. And at that point, it'll maybe like do a query to a bit of z, which helps it narrow things down, right? Like that narrows it down to like, you know, factor 2 fewer input distributions that it has to be worrying about. Okay, so in order to try to prove that, let's go back to the sort of tree view of communication protocols that Xinyu was talking about towards the beginning. Okay, so here's a way you can think about, we have this, you know, once and forever, this fixed communication protocol pi, which is deterministic. And like, let's imagine that like Alice speaks at the beginning. Okay? And like, you know, if you forget about all this stuff for a second, and like in the communication world, like initially, the set of all inputs that Alice can ever have is this n to the k. And the set of inputs that Bob can ever have is this 0, 1 to the kn. Okay. And in a communication protocol, what happens in the roots is like Alice somehow has like a fixed partition of A, all possible inputs, into some A0 and A1. This is squared as like a disjoint union. Okay? And you know, these are all the input, the set of all inputs where Alice would transmit a 0 in the first round, and this are all the inputs where she would transmit a 1 in the first round. Okay? So then she does that in the communication protocol. She transmits either a 0 or a 1. And what I'd like you to think about is like, let's suppose she transmits a 0, then it's kind of like we're going to replace this capital A with A0. Okay, so this now is like the subset of inputs that she might have had she transmitted 0. It's also just like in the rectangle version, like we've gone from like all of Alice's inputs to like some subset of them. And if she transmits 1, we imagine that A gets replaced by A1. Okay. And let's imagine that Bob speaks in the next round. In fact, we may as well imagine that Alice and Bob alternate by speaking each round. You can only change the communication by a factor of 2. Actually, it's not even important, but anyway. Okay, so in this case, like Bob takes, initially he has all possible inputs, and he has some fixed partition into B0 and B1, such that if his input is in here, he'll send a 0, and then we're going to imagine replacing B by B0. If it's in here, we'll imagine replacing B by B1. Here he has like a different partition. I'm still going to write it as B0 union B1, but this is like different, potentially. And he also might send a 0 or 1, etc. Okay, and then Alice has some yet other partition here, etc. And, right. And at the end, you know, there's some last transmission. And then it stops. And like for the purposes of this theorem, don't even think of like pi as computing any function or anything. It's just a tree whereby two sets A, like, and B somehow shrink as you go down the tree. That's it. And a transcript is a path down this tree. That's a transcript. And you know, C is the height of the tree. Okay, we'll see. So let's imagine, okay, we got to eventually build this task, and it's confusing because you have to simulate what's going on in this tree, like what path would be taken down this tree on a random input from one of 2 to the k different distributions. It's already complicated. Just imagine the situation when there's one distribution. So like, let's just think about that for a second. Okay, so let's just imagine simulating, you know, this protocol under, you know, input drawn from one distribution, D, which generates a pair, alpha, which is an input for Alice, and Y, which is an input for Bob. And what I want to describe to you, which I think may help, are there lights on the screen, by the way? So I can just rub the... No.
Hey, good.
Hey, great.
That's a little better.
Yeah. So I want to imagine like 2 ways, like you or a person might imagine like simulating the final leaf that you get to in this protocol when you have a random input drawn from some weirdo distribution. Yeah?
I have a question. Why are you shrinking it to this? Like, I don't understand why like it's straight along with it.
I just want to set it up so that like I want, whether you're going to use this notation whereby if we're sort of simulating a protocol or a communication protocol, I want capital A and capital B to stand for, like, capital A should stand for the set of all inputs that Alice might still have. And capital B should stand for the set of all inputs that Bob might still have. So like at the beginning, Alice could have any inputs, and then she like either sends a 0 or 1 depending on some property of her inputs. And when I say, suppose we decided that she sent a 1, then at that point the set of inputs that she might have is smaller. And it's whatever A0 was here. But then like when I'm here, I want to just say, okay, let's call that capital A. So I want to describe like 2 ways you might simulate, and it's not clear who you is here, but you might simulate this situation. So one is I'll call the eager way. And this is maybe the first one you might think of, which is just, imagine you have full knowledge of D and everything in this story. So you just literally draw from D completely. You draw alpha and Y from B. Okay? And then that's like you use all the randomness up front, and then you just follow deterministically the path down the tree to the end. The path containing the drawn alpha and Y. Okay, you output the final leaf that you get to. Okay? That's one thing you could do. The other way you could do it is what I'll call the lazy way. And this is like where you like really don't want to like do more randomness than you ever have to. Okay? So what you'll do is at the root, you'll start the root, you'll kind of determine, and you'll imagine unbounded computation and unbounded knowledge of D. So you'll just determine the probability under D that alpha would be in A1. And like let's say hypothetically that it's 60%. Great. So then what you do is you like toss a 60-40 coin, and you go right if it comes up heads, and left if it comes up tails. Well, maybe if it comes up 1, and left if it comes up 0. Okay. And so then, let's say it came up 1. So like it's like you decided that you're going to just go down the path. Okay? You haven't decided like everything. Please say it came up 1. So now like, your new A is A1. That's what we said. And in some sense now you also have a new D, which is like D conditioned on like alpha being in A1. And now you repeat this, okay? So like now you're here, and you just determine in a draw from D conditioned on alpha being an A1, what would be the chance that the y, the other part, would be in B1? And maybe it's, I don't know, 30%. So then, like, you spend like one coin flip to like make a 30 versus 70% decision, and maybe it comes up the 70% decision. So then you go this way, and you set B to be B0, and like, you know, now like maybe B has become B0, and like your new D is like, basically D is always D conditioned on alpha being in A and Y being in B for like the current capital A and capital B. So then, you know, you might come to here, and so there's some distribution D conditioned on A being what it is and B being what it is, and you just try to understand what is the probability that the marginal on alpha will be in A1, and you make your decision here and so forth and so on. So it's like the laziest possible way of doing it. You don't commit to anything until you have to. Okay. Now, right. So Q, this query algorithm here, Q, it's trying to do anything, either of these, but it's got an even harder situation because it doesn't even know what the script D is, right? Q just knows that, you know, D, if you will, is one of well, G inverse 0, 0, 0, or G inverse 0, 0, 1. I'm drawing the case where K is 3. G inverse of 1, 1, 1. Okay. You notice it's one of these. Yep.
Even in the previous case, when you knew D,
Yeah.
do you have to like verify whether you're going along the correct path or something? Like, what's like?
Yeah, this is the hard thing to think about. Like, it's like, you have to remember, what is your task? Your task is to, like, come to a leaf whose distribution is the correct distribution under D. Like, one way to think about it is, like, you have to come to a leaf whose distribution is that distribution you get from the eager method, for example.
Oh, okay. So if you know the distribution, then the eager method is already perfect, like.
Yeah, if you know the distribution, the eager method is already perfect.
As is the lazy method.
The lazy method is also equally perfect, but like maybe the lazy method is harder to think about.
Oh, so
like,
you're just trying to simulate the distribution, not the exact path.
In some ways, yeah. Like what's going on here is like it's like the lazy method sort of uses less knowledge of D as you go along. Like it tries to use as little knowledge about D as it can, right? Like here, in order to make this draw, you have to know everything there is to know about D to do this draw. Here, like you don't have to know everything you need to know about D. You just need to know, like, let's say, what is its marginal on the first coordinate, and not even that, just like what is the probability that the first coordinate will be in a set A1. And that is good for Q because Q is a guy that doesn't know a lot about what D is. It just knows it's like in this case one of these 8 distributions. So it's much better for Q to try to use the lazy method than the eager method. Like if Q wanted, it could use the eager method by just querying all 3 bits of Z, in this case, or all k bits of Z, finding out exactly what Z is, therefore finding out exactly the distribution that it needs to simulate, and then it can do the eager method. You know, it's a randomized query algorithm, so it can use coin flip to do all its draws. But that's what it's trying to not do. It's trying to not like do very many queries to Z. Right. So, does that make sense? So, actually, Q's life is not so bad at the beginning. In fact, Q's life is pretty okay at the beginning. Because let's look at like what Q has to do at the beginning. If it's going to use the lazy method, which it will, right? What is the very first thing it needs to know? It needs to know under this distribution, whatever it is, because I don't know what Z is. What is the probability that you know, the alpha part will fall into this fixed set A1? Well, what is, for a given Z, let's say for a fixed Z, what is the marginal on the first part, the alpha part? Right, so like, actually, let's just think about it. Like, what is the distribution G inverse 0, 0, 1, right? We're looking now for all alphas, which are triples of coordinates, like maybe 1, 5, 3, and like all y's, which are like, you know, 3 long bit strings in a row. These have length n. such that when you take the first bit from here, the fifth bit from here, and the third bit from here, you get 0, 0, 1. So it's like all strings that look like 0, star, 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 1, and then star, star, star. Right. So this is an example of a pair. Anything that looks like this, and this alpha is a pair that's in G inverse 0, 0, 1. Right? But somebody please tell me, in the uniform distribution on this set, what is the marginal on the alpha part? Or what is the, if I tell you Z is this, what is the most likely alpha? They're all equally likely. It's the uniform distribution. And that's great. So like in G inverse Z, the uniform distribution on this, the marginal on alpha is exactly uniform. And this is like independent for any Z. Okay. And this is like the query algorithm's dream. Like Q is so happy about this. Like it's the greatest thing could happen for Q. Why? Because it can exactly know this number 100%, even though it doesn't know Z at all. It doesn't know Z at all, but it knows this is literally just the volume of A1 inside this set. So it knows this number exactly. So it can do like one step of the lazy method perfectly. Perfectly. Great, and it made 0 queries. It's also instructive a little bit to think, what would happen if Bob was speaking first? Okay, so if Bob was speaking first, well, then we'd have to ask ourselves, we need to know like this, but with the B situation here. What is the marginal, let's say again, let's fix Z to be this, 0, 0, 1. What does the marginal on Y look like? Is it uniform?
Shouldn't be all ones.
Right, it's not totally uniform, right? Because the marginal on Y, you basically know that like you have 1, 0 here somewhere, and 1, 0 here, and 1, 1 somewhere here. It's actually the exact distribution is like pick a random coordinate here, plunk a 0 in, put a random coordinate here, plunk a 0 in, pick a random coordinate here, plunk a 1 in, and then fill everything else randomly. That's the distribution on Z. Alright, that's almost uniform. I mean, it's very close to uniform if n is very large. Right? So in the reverse scenario, the marginal on Y is nearly exactly uniform. Exactly uniform. And I don't know what the total variation distance is, but it'll be something that's like little o of 1 with respect to n. So that's good. I mean, this is up to like, I don't know, plus or minus little o of 1 with respect to n, whatever that means. And, you know, it's slightly different for each Z, but that's okay. Okay, so for every Z, it's practically the uniform distribution. So you can still do one step here. You know, when you do one step here, you just pretend it's the uniform distribution and do your step. And that actually is causes a little bit of error, but you just pay for it at the end. Okay? So in fact, what we're going to want to do is we'll do every step almost exactly correctly, up to some like maybe 1 over poly k in total variation distance. And we'll sum these errors over all the height of the tree. And the height of the tree is C, and like the communication complexity is without loss of generally most like k log k or something, so it's sufficient for this error to be 1 over poly k. So as long as we, let's say, yeah. So for example, if Alice speaks first, then we can do the first step perfectly. If Bob speaks first, we can basically do the first step perfectly, and we're good. Great. Now, let's say even that like by some, I don't even want to say, think about it. Like, let's say like we managed to actually one step of Alice perfectly and one step of Bob perfectly. I'm not sure it's not quite like that, but let me just try to get into a general state. Then let's say we simulated 2 steps, one for Alice and one for Bob. But like now there's an A and a B that are not the original A and B. So like, let's say after 2 steps, the distribution on inputs Q is trying to simulate is like, the uniform distribution on G inverse Z intersect A cross B. Like, we've kind of boiled it down to like, okay, the true input we're going to imagine is going to be an A cross B. We sort of already decided that correctly and safely, but we still don't know what Z is. So like, this is some weirdo step, and in order to proceed, we have to imagine, what will happen with this D being this distribution. And that's a little trickier because, who's to say that in this weirdo distribution, let's say now Alice is speaking, in this weirdo distribution, the marginal on the A inputs is uniform. Like in that case, we'd be great, but possibly it's not going to be like that. So let me again say, what is Q's dream? Dream is this. Maybe it's done some of the simulations, a couple steps, at least the first step it could do. And now it's sort of boiled things down to some A and B. Its dream is this. It wishes that for all Z in 0, 1 to the K, that could be, in the uniform distribution on G inverse Z intersect A cross B, both marginals are basically uniform. This is what would really be the greatest thing if it happened. This means, up to plus or minus 1 over poly K in total variation distance. This thing happened at the very beginning when A was everything and B is everything. And if this thing happens, it's great. If so, Q can, basically nearly up to this error, perfectly simulate, one more step in the protocol. Like according to the lazy system. Right, so it's like kind of banking on, it's like hoping that like, well, whatever Z is, doesn't matter. The distribution on what, Alice's input would be at this point is the same, namely uniform. Okay. Let me call this stagger. Could that be the case? So it turns out, and I will omit this, this is implied by a different statement. This is like a 3-line calculation. I will omit. It will redefine, by this property. For alpha drawn from A and y drawn from B independently, you plug alpha and y into G, it's point-wise close to uniform. On 0, 1 to K. And this just means each string is output with probability 2 to the minus k times 1 plus or minus 1 over poly k. Okay, so this is some little calculation. Just take my word for it that this is true if this is true. And remember, it's sort of erased here, but like g is the function where basically you take an alpha list of indices, and y is like long string with k parts. This is maybe 3 indices. And like the output is like the first bit of this, the 5th bit of this, and the 3rd bit of this. Maybe y sub alpha, you could call it. Okay. And finally, this is where, in some sense, this is where like the properties of G come in. The fact that it is this like index function comes in. The key technical result is that like if A is like a reasonably randomish looking set and B is a reasonably randomish looking set, then G is kind of like an extractor. Like it'll like pop out a string which is really close to uniformly distributed. So this is the key technical theorem in the paper. Which is that in this picture, suppose A and B are such that when you draw alpha uniformly at random from A, it has some property I'll call quasi-random, which I can say what it is in a second. And when you draw y from B, it has some property called very random. Then G, the output, G alpha y, is pointwise close to uniform.
Maybe another 10 minutes.
Okay.
We have the room until 5, but after that.
Okay. You know, a lot of complex things have happened, so I don't want to kill everybody. So, okay, let me say at a high level, you know, this means basically y as a random variable has almost full entropy. Which in this context is literally the same as saying B is extremely large. B is at least, well, the biggest it can be is 2 to the kn, and like it's at least 2 to the that over k cubed. Here it's important you see why like n needs to be like at least a big polynomial function of k for this to even make sense. This is like saying, it turns out that like, so remember alpha A is a subset of k coordinates, and this quasi-random is like for all subsets of j of k, if you draw alpha in this way and then look at its projection onto the j coordinates, this random variable has a lot of entropy. And let me not multiply everything. So it's like two different notions of being randomness. Here, like y should be like almost full of entropy. Here, alpha, it doesn't have to be like have tons of entropy, but like even restricted to any set of coordinates, it should have like a lot of entropy.
So why can't I just choose j to be all of k? Like
It sounds like a stronger property,
right? It's a lot of entropy vis-a-vis the size of j.
Yeah.
So like, right, so like the most alpha j, the most, it's actually min entropy. The most min entropy this could have is cardinality of j times log n. size of the domain in which it lives is n to the cardinality of j. And like this, a lot of entropy is to say that it's at least 0.1 times this. So like on all single, like when you take a draw from alpha and just look at the marginal on any single coordinates, the most entropy it could have is log n, and it should have at least 0.1 log n entropy. And if you look at its marginal on any two coordinates, they should have at least 0.2 log n entropy.
So still, this is a stronger property than very random, like up to the exact constants you use, right? If you take J to be like the entire set.
Yeah.
Right. I mean, here it's just that B has a.
No. Here, like it's min entropy. So this is to say that the min entropy of y is at least the maximum it could ever be is Kn, and it's like Kn minus a little bit. It's like Kn minus 3 log K. Where here it's like, it's not like, you know, it's kind of like 10% of what it could be, and at least 10% of what it could be. And here it's like almost full minus.
So up to the exact constants, right? Like here's like 0.1, here it's like 1 minus a little more than 1.
Right. But you know, it's all a delicate dance, so like it's important that these are defined the way they are. And right, so their key technical theorem is that this is exactly true. And the proof of this, which I of course will not be doing, is like 4 pages of like Fourier analysis. Of course, I love that stuff. So like me and Xinyu thought about it, and we can get it down to maybe like 2 pages by using some Fourier power. But anyway, that's like the second half of their paper is this stuff. And like this to them is like the key innovation. Like this is the thing that like is like the improvement over previous work. Which is like hard for me to like accept, right? Because like I was like, okay, I'm okay with this stuff, but like all the previous stuff about simulating trees and everything, like that was crazy to me. But like Goose, Potassium, and Watson were like, yeah, that's fine. I mean, this was the hard part to them. Okay, so I'll stop in 5 minutes, but let me just say a little bit more, because in a way we haven't even got to the key part. So.
Why don't you take 10 minutes?
No, it's okay. I mean, I have, it's going to perfectly stop in like 5 minutes. So, right. So Q is doing this like lazy simulation of the tree under like this distribution. And as long as capital A and B are such that they have like enough entropy in some appropriate sense, then this is true, which means this is true, which means like the marginal of the distribution it's trying to simulate on both A and B is basically uniform. And so I can do like one step in the lazy evaluation. Great. But of course, like every time you do one step in this like tree over here, which I erased, right, capital A shrinks or capital B shrinks, and that obviously has the potential to like screw you up here. It turns out that like on average, B does like not shrink that much. And that's because like every time, let's say you're doing like the lazy evaluation and you're on a Bob speaking step, right? So like Bob partitions the current B into like 2 parts, like maybe one is of size 80%, one is of size 20%. And then you follow the 80% one with probability 80%, you follow the 20% one with probability 20%. So like you're always like more likely to go into the bigger parts. If like Bob has a partition into like one almost everything part and one teeny tiny part, you're probably not even going to go into the teeny tiny part. And that means that like Bob set B, it just sort of naturally with high probability stays pretty big. So basically it's very easy throughout the course of the proof to just show that capital B never gets too small except with very low probability. The hard part is this like A side, it's like with this crazier quasi-randomness. And yeah, that's the key challenge. Like what happens? You're going along in this simulation. If like A is nice and quasi-random, and then like you do one lazy A step, and like boom, the new like A is not quasi-random anymore. And maybe the picture is like, imagine K is 2. Okay? So like all of the living inside n squared, which is like a grid. Like A is a set of points, so like maybe it's these points. And like, maybe that's the new A. Now this new A is nice and quasi-random. Like, you know, it's a good like number of points, so like, you know, it's got a fair amount of entropy. And like if you project it this way, it's got a fair amount of entropy, and you project it this way, it's got a fair amount of, you know, mean entropy. But like maybe this is too good. Like maybe you get to the new A and it looks like maybe this. It's like all these purple points plus like these black lines. And like this is like alpha 1 equals 5. Maybe this is the new A, these purple points plus these black ones. And this is very bad because like in the first coordinate, there's one outcome, 5, which has like way too much probability. So like A, the uniform distribution on A, restricted to the first coordinate, has like one value, 5, with like enormous probability, which means it has high or low, whatever, the bad side of miniaturing. So what do? Well, basically, the simulator does like an eager thing. Instead of following the tree, it like decides to eagerly decide whether the draw from the distribution is in like this set or the remainder of the set. And it kind of splits the set up into like pieces that are quasi-random again, so that it will be able to proceed in the future. But if it decides that it's going to be in this set, it kind of wants to like live in one fewer dimensions. Like this set is quasi-random in like in the one-dimensional space, but like not in the two-dimensional space. So in order to like proceed and have everything be quasi-random, like it wants to say like my new world is just one dimension less. It's like one dimension less coming from the fact that I want to say like my draw I've like fixed that alpha 1 is 5. And basically, you know, I'm going to end in 20 seconds. Like this is where the query algorithm finally makes a query to Z. Like if it, you know, doesn't like an eager step and decides that like, okay, we're going to restrict, you know, it turns out that we want to like live in this world where alpha 1 is 5. Then, what would be if like this was 5? Then basically you need to find out what Z1 is. In order to like sort of restrict everything to the case where the first coordinate is fixed, you need to find out what Z1 is. So you spend a query to get what Z1 is, and let's say it's 0, and then it's like you fix Bob's input to have a 0 in the 5th position here, and then having done that, like everything about coordinate 1 out of the k coordinates is now fixed, and you can kind of proceed like it's back, like kind of like you're back to normal. And so the reason you eventually end up making queries is because these sets A that you restrict down to are not quasi-random. They kind of like bunch up in like some coordinates. And then like by making a query, it's kind of like you like unbunch things up and you get back to the quasi-randomness and you go on. And so there's some analysis to understand like how come, you know, this bunch up doesn't happen too often, and like so why you only make about C queries, or about C over log n queries, but on average, like you have to query about 1 time or a constant number of times per height of the tree. The end. It's much longer than that, but thanks.
Is there any natural way to say like, why that 1 over log n comes from?
Yeah, let me check my notes. So overall, you have a potential function, which is the you look at the min entropy of the set A that you currently have, or more accurately, you look at like the maximum it could be given its current dimension minus its min entropy. Like how close is it to having full min entropy? This is like a potential function that like can go up or down, but it's not negative, so it never goes below 0. And somehow, as long as you're going along, you're not making any queries, and everything is staying quasi-random, then this like changes by at most a constant for every step on average, it turns out. On the other hand, like, in other words, it increases by at most a constant. Like this is a measure of like how far away from being super random A is. So like, you know, if you do some steps, like A kind of gets a little bit worse, it goes up by like a constant at each step. But like when you do this and like make a query, it actually gets better because when you make this partition, like the extent to which like this black set is kind of random looking within its single coordinate, it turns out like it's notably better than the extent to which the original set A was random looking in its 2 coordinates. And that comes from the fact that there's a 0.1 log n written here somewhere. So like, it turns out that like when you do this like partition and like go either into this set or this set, like when you make one query, on average, this goes down, like you get more random by like a 0.1 log n amount. So basically, every time you do a query, this potential function, like how far from random A is, it goes down by theta log n. And every time you do like one round of the communication protocol, it goes up by like a constant. So that means like the number of queries you can ever make can never be more than the total number of rounds C divided by log n. Any more questions? All right, so next week we'll do the quantum version.